Hi everyone. I am Dazhen Deng from Zhejiang University. Today, I will introduce a study about the design patterns of composite visualizations. With the development of information technology, the data in the industry and business becomes increasingly complex, such as high-dimensional data, spatiotemporal data, hierarchical data, and other heterogeneous data. However, the basic visualizations familiar to the public are relatively limited in representing complex data. Therefore, in order to visualize complex data for analysis, many visual analytics systems have employed composite visualizations. Composite visualizations refer to a design strategy that exhibits complex data by combining multiple basic visualization types through overlaid, nested, and other patterns. Composite visualization is very suitable for visual analytics, because it can show the features of complex data in a limited screen space. Javid and Elmquist have defined and explored the design space of composite visualization in an early publication. Recently, several studies collected and annotated visualization designs from the publications. Reflected by the authors, a key challenge is to identify the exact visualization types for each view, which is usually composed of multiple different visual elements. These studies highlight the importance of revisiting the existing designs and proposing a fine-grained and practical taxonomy for the composition patterns for downstream analysis and research. Therefore, we wanted to quantitatively study how composite visualizations are designed in existing visual analytics systems. Questions to be answered include: which basic visualization types can be composited? How are they composited? What are the advantages and disadvantages of different composite visualizations? It lacks a comprehensive review and quantitative analysis of existing visual analytics system examples. In order to review and analyze composite visualization, we first give the definition of composite visualization. Composite visualizations are defined recursively. Its basic components are the basic visualization types. Composition pattern characterizes the spatial and semantic relationships between basic visualization types. As shown in the figure on the right, we provide a nested composite visual data structure. To construct a corpus, we collected a total of 863 visual designs from IEEE VIS from 2006 to 2020. We first label the locations and types of the basic visualizations. Next, we analyze the composite relationship between basic visualization types. Finally, we summarize the patterns and deliver a design space. The taxonomy of composition patterns is shown in the figure, which contains 2 levels and 8 classes. Next, I will detail each category and the division rules between categories. The first level is divided according to spatial relationships. Juxtaposition means that there is no overlap between visual components. In contrast, overlay refers to the spatial overlap between visual components. Nesting is different. There is spatial inclusion between its components, where some are placed inside other components. For juxtaposed visualizations, we divide it into 2 categories according to whether the component type structure is the same. For the visualizations of the same component structures, we further divide it into 2 types based on symmetry principles, which are repetition and mirror. Repetition visualization refers to repeatedly enumerating components of the same type. We counted the number of repetitions of these repeated components and found that the repetition number showed a long-tail distribution, with the maximum number exceeding 50. When the repetition number is small, the components are generally used as the main view of the system. When the repetition number is large, the visualization is generally used as a small multiple to support users to quickly browse a large number of data items. When the number of repetitions is relatively large, some designs will use shared coordinates to reduce the number of components and facilitate comparison. Repetition visualization is easy to explore and compare multiple objects, easy to understand and implement, but when there are too many, unnecessary information needs to be hidden to reduce redundancy. Mirror pattern refers to 2 components of the same types that are symmetrical about a certain coordinate axis. Due to the metaphor of the mirror, in visual analytics, the mirror pattern is often used for visual comparison. We have shown two examples that employ the same structure of components that invoke comparison. Although both repetition and mirroring are commonly used for comparison, in practice neither type of design is suitable for precise and nuanced comparison tasks. Stack is different from the previous two patterns in that its visual components are of different structures or types. Two components share common visual dimensions that allow them to be stacked or concatenated together. Here is an example of a visualization of the map, heat map, and histogram. The visualizations are stacked through the same dimension. In this visualization, different components have different features. The components can be categorized into auxiliary components and main components, and auxiliary components generally serve as a visual overview of the main component. In addition to the grid layout, we also found a novel linear layout that can connect multiple different types of visualizations through their shared boundaries. Overlay visualizations are divided into two categories based on whether the coordinate axes are related. When the coordinate axes are related, we divide them into two categories, coaxis and coordinate according to the data relationship. Coaxis means that two subcomponents share the same coordinate axis. Here are some examples of common coaxis visualizations. Components of coaxis visualization may block each other, so important information should be placed on the upper layer. Inconsistent coordinate axes should be avoided during design. For example, sometimes there are dual y-axes, which can easily lead to misunderstandings. In coordinate visualizations, the parent component provides reference to the child component as the coordinate axis of the child component. The picture shows several examples of coordinate visualization. The most common situation is to place the node link diagram on the map. When designing a coordinate visualization, since occlusion between parent and child components is unavoidable, occlusion between child components should be minimized. For the case where the coordinate axes are not related, we distinguish two design patterns based on whether there is a visual connection between the parent and child components. They are annotation pattern and large panel pattern. Annotation pattern refers to that the child component is connected to the parent component through a visual link to explain the specific data item of the parent component. The large panel pattern refers to placing the child component directly on the parent component, and there is no visual connection between the two. Nested pattern means that some visual elements of the parent component are used as the canvas of the child components, and the child components are embedded into the visual elements of the parent component. As shown in the figure, the nodes of some node link diagrams can be expanded to place additional visual elements, such as heat maps, matrices, and bar chart. The nested design implies hierarchical information, which is easy for users to understand. When designing, subcomponents should be relatively common and simple. When necessary, we can consider deform the visual elements of the parent component to make room for the child component. We counted the occurrences of all composite patterns. Overall, the juxtaposition is the most frequently occurring composition pattern. It may be slightly different from your imagination. Nesting is the second most among them, slightly more than overlay. Repetition are the most frequently occurring subcategories. After our analysis, we identified two future research opportunities for composite visualizations. From the perspective of implementation, most composite visualizations are implemented using low-level programming languages such as D3. Future studies can consider extending the existing grammar library to support the generation of composition patterns. Existing grammar libraries only support relatively basic composition patterns and visual elements. For example, a grammar library for common composition patterns such as nesting can be developed to improve the efficiency of visual analysis system construction. In addition, the effectiveness of complex designs in visual analytic systems has often been criticized for long. Empirical studies can be conducted for composite visualizations. This study gives a taxonomy of different composite patterns. Subsequent research can design user studies for different composite modes based on the classification, evaluate their effectiveness, and provide guidance for subsequent visualization design. We hope that our study can give an overview of the existing composite visualizations and inspire future studies on the automatic generation of the visualizations for complex data analysis. Here is the link to our website and data. Thank you for listening.